we actually have a little time to start section 7.2. And so I just wrote down a couple of well-known trig identities for review at the top here. Sine of 2x equals 2 times sine of x times cosine of x. And sine squared of x is equal to 1 minus cosine 2x over 2. And cosine squared of x is 1 plus cosine 2x over 2. I didn't bother writing down the most well-known trig identity, which is that sine squared plus cosine squared equals 1. But notice if you take that last line, the one with the cosine 2x's, and add those two fractions together, then the cosine 2x's cancel. You get 1 minus cosine x plus 1 plus cosine 2x, 1 minus cosine 2x, sorry, and they cancel, you get 2 over 2, which equals to 1. So we do have cosine squared plus cosine squared equals 1 also. And then there's the versions of that one where you can divide through by sine squared and cosine squared and get ones with secant squared and tangent squared. Okay, so 7.2 sort of continued, and this is sort of the first thing. We're going to start with an example. 7.2 is about integrating, find the antiderivative for some trig functions that have sine and cosine to powers. And the first strategy is basically just u substitution, but a little bit fancier. The first thing to do is to try to write things in terms of everything in terms of cosines, except for one last sine of x. That lets us do a u substitution. So I see that sine to the 5 looks like sine squared of x squared, because that's sine to the 4th, times another sine x. So I pulled out one of the sines. This works really nicely when you have an odd power of trig. So sine to the 5, I pulled out one of them, and then I went ahead and made the sine to the 4 into sine squared squared. The cosine squared, I didn't need to worry about it since it's already a cosine. And you can see down there what the strategy is, why I'm rewriting sine to the 5 like this. Then again, sine squared plus cosine squared equals 1. So I have sine squared equals 1 minus cosine squared of x. All right, now all that trig, you start out with just doing some trig identities, works nicely because if I let u equal cosine x, then du is going to be sine x, well, negative sine x, so I'll have to keep track of that minus, and negative du is equal to sine x dx. That lets me deal with that whole problem using u substitution. I can put in a u for every single cosine, so I have 1 minus u squared squared, I have u squared, and then I have that last sine of x dx, which is just going to be a negative du from the substitution. So this worked because I had an odd power of sines. So then when I had an odd power of sines, I made u equal cosine, and that let me replace all the cosines with u's, and I have that one last sine that became the du. Now I have to work it out now. It becomes just a polynomial of u's, but I do have to do FOIL on that first part. So I'll have 1 minus u squared from the inner and outer, giving me 1 minus 2u squared plus u squared squared, or u to the 4th, all times u squared. And I took the extra minus and moved it out front for later. Then I have u squared minus 2u to the 4 plus u to the 6, multiplying the u squared through the parentheses. And then I can raise and divide all along. U cubed over 3, u to the 5 over 5, u to the 7 over 7, and that's it. However, that's not really my answer because u is equal to cosine. So I go back through and plug in cosine for each of those. Cosine cubed x, cosine to the 5x, cosine to the 7x, and of course I had to keep those denominators I got from the raise and divide. And be careful with the minus sign. It made the first one negative, the second one positive, and the last one negative when I multiplied the negative through. And you can check that that works out. Interestingly, a lot of times if you do this problem on a computer, it'll give you a much more complicated answer. Some programs may be smart enough to get this simple answer, but this might be one that you can do better by hand than calculator.